Very well.
Let me go to full screen. Yeah.
That works. Sure.
And welcome everyone to this webinar. I would like to talk today about gas engines and CHP for distributed power and how we make them ready for hydrogen. Before we go directly to hydrogen, I would like to introduce a little bit our applications, what we do. And on the very left side, you can see that 55% of our engines in the EU are already running on climate neutral gases, such as biogas and others. That's already a huge achievement. So when we talk about the 55, Fit for 55, we have done some contribution here already. Going forward and tomorrow, we need to transfer also the other gas engines running on natural gas today to carbon neutral fuels like biomethane or hydrogen, and continue with biogas, a very successful application for our technology. It will also be the usage of CO2, like for greenhouse gases. Here biomethane is the more preferable technology or the fuel. And for CHP, it could be hydrogen replacing natural gas. When it comes to hydrogen, we have already several projects installed. And we have several projects under development that will run on 100% hydrogen, most of them in Europe, but also some in Asia and in some hydrogen blending in Americas. We have a huge installed base in Europe. All over, we have delivered 25,000 engines, and 55% of those engines are in Europe. And as I explained before, 55% of the European engines are running already on renewable gases. Okay, a little bit to introduction, where we're coming from. Recently, earlier this year, we have published through our Eugene Association in Brussels, this study about residual load requirements in 2050. And the outcome of this study was in 2050, there is still a huge demand for residual power generation. So in times when renewables like wind and solar, hydro are not delivering. And here's an example of 3 weeks in January in 2050, how it could look like. And we can see in these 3 weeks, 109 terawatt hours of residual load is required that will mainly come from gas power plants and typically running on hydrogen. 2 terawatt hours are only available for recharging batteries. And the capacity that is required is 366 gigawatt of residual power plants, and only 35 gigawatt can come from demand-side management, and only about 60 gigawatt could come from hydro pump storage. But the hydro pump storage, as we know, it works very good and has a very short response time, but typically it does not last 3 weeks. This can only be done with gas power plants. What we see and what we have heard already before is the electrification. Electrification will come from electric vehicles, and a lot will come also from electric heat pumps that will drive the demand and increase the demand on the distribution side, of the electric grid. And our CHPs are installed exactly at these places, at the distribution side, typically at places where there is a need for electricity and heat for district heating, for larger buildings, and so on. So that could be, or that will be, a very nice combination of local CHPs and covering or supporting the growing electricity demand. Here's a little bit more how gas engines and CHP, decentralized CHP, can work together with heat pumps in the future. Ideally, electric heat pumps run with renewable electricity, when electricity is coming from the grid, from wind and solar. But there are times where there is no wind and no solar in the wintertime, but a lot of heating is required and the heat pumps need to run and provide heat. Here, the combination with electricity from decentralized CHP or even from large power plants, from gas turbine power plants, from centralized installed power plants could help out. And there's also a view, what about using the hydrogen directly for heating? Here, this is explained a little bit better. When we have renewable power on the left-hand side, this can be directly used for running a heat pump. And then you get out most of the heat out of this originally renewable power generation. But when there are times the renewable power is not available, we need to switch to hydrogen. Hydrogen, green hydrogen, need to be produced first out of this renewable power at other times when there's an oversupply of renewable power. Hydrogen is then stored, and with this hydrogen we can run a CHP or a large centralized power plant and then use the electricity to run heat pumps. But of course there are losses in between, and therefore we don't produce as much heat with the heat pumps as we do when we use the electricity from renewables directly. But still, it's much better than using hydrogen in a boiler and burn hydrogen for producing low-grade heat with less than 100 degrees Celsius. This is the worst thing we can do and utilize hydrogen. We should use hydrogen in a much more efficient way, like in a CHP plant. Going to the next, but hydrogen, how we produce hydrogen today is typically local production and we do local storage. What we need going forward is, of course, a hydrogen network to transport and distribute hydrogen via a pipeline grid similar to what we have today on natural gas. What would be the early movers, the early adapters for hydrogen? We have looked to our segment, what could be our first applications where we could use hydrogen CHP and hydrogen distributed power. And one of the very interesting applications is data center, backup solutions for data center, replacing diesel backup with hydrogen backup. Other applications could be microgrids, where you have local hydrogen production, hydrogen storage, and reconvert hydrogen when renewables not covering the electricity demand. Industrial applications or island modes applications could be early adapters. Before we have a more sophisticated hydrogen grid and network to distribute hydrogen in a wider range, and then we could run bigger balancing power plants or CHP power plants, bigger CHP power plants that run more continuously, not only in backup, more continuously during the winter time when we have the huge gap, as we have seen before on this chart from the Eugene study. I give you a couple examples how we use hydrogen in our engines, what we have done in the past over the last 30 years and going forward. This chart explains what we have done over the last 30 years. We have done a lot of projects, actually 90 projects in 28 countries around the globe, with engines running on high hydrogen fuels. And the very left one is an example from Austria in Krems, at Krems Chemie, where the engines run on a fuel that contains more or less 95% hydrogen. These engines are running more than 25 years, and all of these engines have achieved 200,000 operating hours meantime. In the middle, you see a syngas application where in this case it is waste is gasified, but can also be biomass, and this gas has a typically 30 to 40 volumes% of hydrogen. And then there's a demo project in Argentina. I will explain a little bit more to that. And going forward is 100% hydrogen application, and we already have projects for that applications. The project in Argentina, this was developed 15 years ago and demonstrating green hydrogen production, underground hydrogen storage, and re-electrification of the hydrogen. This is an area in Argentina where there's a lot of oil and gas production. We have installed a lot of engines in this area. And this area is also an area where there's a lot of wind potential. There was a small wind power plant installed already 15 years ago with 6 megawatts, with a very, very high capacity factor, over 50%. And this wind power is used to run electrolyzer producing hydrogen for underground storage and re-electrification in a gas engine. There was blending of hydrogen up to 42 volume%. This has been done over 15 years now. The engine is not running at 100% hydrogen, just between 0 and 42 volumes%. But the engine is operating more than 100,000 hours in the last 15 years. These are some pictures where you can see in the middle here the electrolyzer installation. On the very left-hand side, you see the genset container, which is a 1.4 megawatt gas engine. Then you have also the oxygen plant. Yeah, it's a very remote area. Okay, just 2-3 years ago, we demonstrated then the first CHP engine that can be, or that was converted from natural gas operation to hydrogen operation. And we demonstrated with this conversion to 100% hydrogen operation that all the engines in the field can be converted from gas operation to hydrogen operation when hydrogen is becoming available. There are some technology changes on the engines required, like a port injection and the cylinder selective combustion control system. Also a wastegate was installed, but this can also all be done in the field, and the engine can be continuous to run on hydrogen later on. There was some performance shown here on the left-hand side. When running on pipeline gas, this engine was optimized on total efficiency over 93%. We did some blending of hydrogen with 20%. That could typically happen in pipeline gas. The total efficiency didn't change, output didn't change, but when running on 100% hydrogen, this engine, because it's designed for natural gas operation, was reduced in power to about 600 kilowatt. But total efficiency also did not change really. And very interesting was the NOx emissions, they did go down from 250 milligram to less than 100 milligram. That's another advantage when running on hydrogen. Another project similar to that, and a similar engine, the 420 engine, will be installed in South Korea, running on industrial hydrogen that comes as a byproduct from polypropylene production. This engine was already shipped to Ulsan in South Korea and will go in operation by the end of the year. It can run on pipeline gas as well as 100% hydrogen, producing about 1 megawatt output and using the exhaust heat to produce process steam for the factory. The next project is a very interesting one. This is a data center. As explained before, data center are one of our targets for hydrogen engines, and this is the first data center that will run with hydrogen engine as a backup. Installed in the Netherlands for the data center Eindhoven. North Sea is the operator of this data center, and they are operating about 15 local smaller data centers, also some in Germany and one in Switzerland. They want to become carbon neutral, 100% carbon neutral by 2030. And they use 6 of these hydrogen engines in the data center Eindhoven to replace a typical diesel backup. Yeah, diesel is the typical backup solution for data centers. In this case, they use hydrogen engines. But hydrogen is stored locally, and there are limitations in storing hydrogen. So the engine can run maybe 1 hour on hydrogen. If the electricity interruption to the data center takes longer, the engine can switch smoothly to natural gas operation and continue providing backup power to the data center. Once the data center is connected to a hydrogen network, then this switch to natural gas is obsolete and the engine can continuously run on hydrogen backup. And one more project in Serbia, where this customer is investing in a solar plant, in a bigger solar plant with 12 megawatt. They have then problems with the feed into the network. So they're installing a battery system with 8 megawatt hour. But in addition to the battery system, they're installing an electrolyzer system to produce hydrogen. They have then a local storage. And then they transport this hydrogen about 200 kilometers north of Belgrade, where they install a 420 1.3 megawatt CHP engine. And this engine can run on natural gas and 100% hydrogen when hydrogen is available from the solar plant. This engine then provides power for a fast charging electric vehicle charging station. And here they have the other problem. They cannot have enough power from the grid for these fast charging stations. So they need local power production. The heat is used for a nearby commercial building. And in Germany, we don't have a demo project yet, but we have done an announcement and worked together with our largest customer. This is Stadtwerke Kiel, where we recently, a couple of years ago, installed 20 large engines with a total plant output of 190 megawatts. This is a CHP plant replacing an old coal plant. And that plant is in operation a couple of years now, since 2019. And in 2035, they want to convert this gas power plant to hydrogen operation. So until 2035, they expect to have enough hydrogen available through a pipeline supply and then switch the engine and convert the engine power plant from natural gas to hydrogen operation. So, what does it mean ready for hydrogen? When we talk about ready for hydrogen, this means our engine can be converted to 100% hydrogen in the future. So all the engines we deliver today can be converted to 100% hydrogen operation when hydrogen becomes available and replaces natural gas. In the meantime, if there is some hydrogen blending to the pipeline system, the engine can run continuously and smoothly with a hydrogen content in pipeline up to 25%. And we have already one engine that is available to run on 100% hydrogen, as explained before. Going forward, we're working to have all our engines. We have five type of engines, from very small engines to big engines like 10 megawatt output. And we want to have all these engines that typically run on gas, natural gas or biogas, available as hydrogen engines. One engine is already available with 1 megawatt output. The next engine, which is much bigger in output, is the Type 6 with up to 3.5 to 4 megawatt. This will be available in 2025 and the other engines until 2030. Then we have a complete portfolio with hydrogen engines. With these engines, we are building power plants, typically multiple engine applications. And with the Type 4 today, we can provide hydrogen power plants up to 20 megawatt. In the future, in 2025, we can do bigger power plants with about 60 megawatt output, 4 megawatt to 60 megawatt, installing multiple Type 6 engines. And going forward until 2030, we have then the capability to do large power plants all the way up to 200 megawatt that can run on 100% hydrogen. So, in summary, our engines running today on natural gas can be converted to hydrogen operation later. We can do some blending up to 25%, even up to 30 volume % in the natural gas. We can do local blending if the engine sees or is provided with two different gas streams, one hydrogen and one natural gas, we can do dual gas engines that can run on 100% hydrogen, 100% natural gas, optimize it to natural gas or hydrogen, depends what is the primary fuel and what is the backup fuel. And going forward, we will see then pure hydrogen engines. That is the future until 2050. There will be no natural gas anymore. So then we can run on hydrogen, but continue also with biogas and biomethane. That's my summary slide, and I thank you very much for your attention and looking forward to a good discussion later. Thank you.
Yeah, Klaus, thank you very much for the presentation. Questions we're going to do afterwards in the joint panel session.